All right, everyone. Welcome to the next seminar. From today, we have Pablo Quílez, who's a postdoc at DESY, soon to be moving to UC San Diego. So Pablo originally did his undergraduate degree at the fantastic University of Zaragoza, where I was also at for some time, not overlapping, but nevertheless. He then moved to Madrid for his master's and PhD before starting his postdoc at DESY. Where he's done some really interesting work on axion theory and phenomenology, which he's going to tell us about today. So thanks a lot for agreeing to give this seminar, Pablo, and I'll leave it with you.
Okay, so good morning, afternoon to all of you, and thank you very much for the invitation. I'm very happy to discuss some physics with you. So today in this seminar, I'm going to talk about two different topics. First, I will try to explain you these two works that we did in collaboration with Luca Di Luccio, Belen Gabela, and Andreas Ringwald, in which we try to explore the possibility of the QCD axion that solves the strong CP problem to be much lighter than usual, right? So we wanted to explore whether it is possible for the QCD axion to be way lighter, right? And then on a second step, I will just briefly mention a new idea that I got with my office mate that we will actually upload today to the archive. That is that we realized that the experiment phaser at the LHC is automatically, without doing anything, a light shining through wall experiment that could, in principle, look for axions. So I will also briefly talk about that. So let's start with the QCD axion. Oh, sorry, let me put the timer so that they don't. So it's, by the way, so don't hesitate to stop me at any time, right? So let's try to make this dynamical. So in my opinion, the QCD axion is one of the most motivated scenarios beyond the standard model. And the reason is that the QCD axion is a really simple theory that basically involves one free parameter, that is the axion decay constant. And it's able to solve two major problems of the standard model, despite its simplicity. In particular, it was originally proposed to solve the strong CP problem, but then later on, we realized that it is also an excellent dark matter candidate. And unlike other dark matter candidates, the QCD axion is still very much alive. As you can see here in the plot, one of these fantastic plots by Kieran, by the way, in the plot of the axion coupled to photons with respect to the axion mass, we see that only really recently experiments like ADMX has started to scratch the surface of the interesting region of the parameter space for the axion. However, this situation is going to dramatically change in the next decades because there's a really strong experimental program that will in the future either find the axion or exclude large regions of the interesting parameter space, as you can see here in all these different projections of different present and future experiments. So I think this is a really interesting moment, right, to work on axions, because we not only can study really interesting phenomenology, but also in the near future, we will be able to test it. So let me briefly comment about how the axion solves the strong CP problem. So the strong CP problem can be summarized with the observation that we don't really understand why the strong sector doesn't seem to violate the CP symmetry. Because we know that CP is not a good symmetry of nature because it is explicitly broken in the weak sector. And one would expect that it could also be broken in the strong interactions through this kind of operator, the G dual operator. However, when we measure CP violating observables like the electric dipole moment of the neutron, what we find is that this parameter needs to be extremely tiny, of the order of 10 to the minus 10. And this is basically the strong CP problem or the strong CP puzzle, let's say. This is a hint of where the new physics could lie. And we would like to understand why this parameter is so small. So one of the most elegant solutions to this puzzle is the so-called axion solution, that at the end, one way of looking at it is through the following observation. If this parameter, instead of being just a number, were to be a scalar field, then the strong dynamics of QCD would generate a potential for this scalar field that forces the minimum of this scalar field, that means the BEV of this scalar field, it forces this BEV to be in the CP conserving point. This means that whatever initial theta I start with, then the axion will take a vacuum expectation value that exactly cancels, and therefore at low energies, I basically have no CP violation. So this is how the axion, that is this scalar field, solves the strong CP problem. And one of the consequences of most of the QCD axion models is that the mass of the axion, that is nothing but the second derivative of this potential that is generated by QCD, follows this relation that depends on the mass of the pion and the mass of the up and down quark. So is there? Okay, that's just some noise. Okay. So let's have a look at so one of the predictions of the invisible axion paradigm is that both the axion mass and the axion coupling to photons are inversely proportional to the axion scale. That's why in the usual plot of the axion coupling to photons with respect to the mass of the axion, we expect the QCD axion to live within this yellow band. And typically, any other particle that lies in the white region of the parameter space is typically called an axion-like particle. That means that it's a pseudo-Goldstone boson that has similar properties to that of the axion, but that in principle is not related with a solution to the strong CP problem. However, given this strong experimental program that in the near future will prove all these regions of the parameter space, I think it is important to take one step back and really wonder whether we should only expect the QCD axion in this band, or whether there are other possibilities, and whether we could also explain the strong CP problem, solve the strong CP problem, with an axion that lives in the white region of the parameter space. And indeed, this has been pursued in the past, and there are a lot of papers that try to construct models in which the axion is either photophilic or photophobic. That means moving the QCD axion band upwards or downwards by enhancing the Wilson coefficient that relates this to the axion coupling to photons and the 1/FA.
Hi, Pablo, just 1 second. There's a black box which is appearing on the right-hand side. I think you may have a zoom window there. Maybe you can move it to like a non-obstructing. Yeah, that one. Yeah, so that appears as like a big black box to us.
So maybe, I don't know, I can put it here. I don't know. Maybe here it bothers less there. Like
yeah,
this,
I think that's better. Yeah.
Okay, cool. Yeah, so there has been already some effort in order to build these models that go beyond the usual QCD axion band. But and as I was telling you, one strategy is to move in the vertical direction the QCD axion band by either enhancing or suppressing the coupling to photons. Another alternative that also has been pursued in the literature is to build heavy axion models. That is, models in which there are new sources for the potential of the axion, right? In which the QCD axion band is moved to the right, that therefore you're attacking this other part of the problem. However, little effort has been devoted in constructing models in which the QCD axion is actually lighter than the usual prediction. And indeed, this is, in terms of the experiments and the phenomenology, this would be really interesting, because this is actually the region that all these experiments will prove in the near future. And this will be the main goal of this work that I'm going to present you. But before going to the specifics, let me ask two general questions that I picked among within the invisible axion paradigm. So the first question is, could Casper electric phase 1 detect an axion? So Casper electric is a dark matter axion experiment that aims at detecting a time-dependent electric dipole moment of the neutron. Indeed, in order to solve the strong CP problem, we need the axions to couple to gluons through this coupling. And as a consequence of this coupling, we obtain that the axion couples to the EDM operator. And if the axion is dark matter, this would induce an oscillating electric dipole moment of the neutron. And this is what this experiment, Casper electric, is looking for. However, what happens is that the axion mass also comes from exactly the same coupling. This means that there's a one-to-one correspondence between the axion mass and the axion coupling to the EDM in the vanilla, let's say, invisible axion paradigm. So then a pertinent question is, how could one interpret a positive and hypothetical positive signal of Casper electric in this region of the parameter space? So if Casper electric detects something here, then through this formula, we can obtain what is the correspondent, and we want to interpret it with an axion, right? We can compute what value of FA it corresponds to. But then once we plug this value of FA in the mass of the axion, what we see is that the axion will be automatically heavier and therefore out of the reach of Casper electric phase 1. This means that Casper electric phase 1 it cannot detect a real axion, because the region that it explores is somehow a bit unphysical, because an axion with that coupling would automatically be heavier. This, as we will see later, will change in light of these kind of models in which the axion can be lighter. So another question that one may ask is, can the QCD axion be fuzzy dark matter? So in order to explain some small scale structure issues of the dark matter paradigm, some people have explored the possibility that dark matter can be an extremely light boson. By extremely light, I mean of masses of the order of 10 to the minus 22, 10 to the minus 20 electron volts. And since the QCD axion is also a really light particle, right, a natural question would be, can the QCD axion be this kind of dark matter? But once you plug in the numbers, you see that in order to get such extremely light masses, one would need a Transplanckian decay constants. And therefore, in quantum field theory models of the axion, one cannot obtain the QCD axion as a fuzzy dark matter. Okay, so now with this introduction, let me move to our project, that is an even lighter QCD axion. So, as we have already commented, the mass of the axion and the potential of the axion comes from the non-perturbative dynamics of QCD. And this is the formula of the axion potential. And as I have already commented, it is crucial to solve the strong CP problem that the minimum of the axion corresponds to the CP conserving point, the point in which the effective theta parameter is basically 0. This is telling us that it is a bit dangerous to change the potential or the mass of the axion, because any new contribution to the potential in principle could spoil this minimum, right, and therefore could spoil the solution to the strong CP problem. This means that in order to make a lighter axion, we need some degree of alignment, right, in order to not to spoil the minimum. And then on top of that, we need some degree of cancellation, because we know that at least we will have the contribution from QCD. And then one needs that the extra contributions somehow cancel the QCD contribution. This may seem as something completely fine-tuned, and maybe this is the reason why not so many people have explored this. However, I want to convince you now that this can be done in a technically natural way through a symmetry. So let's consider the following possibility. Let's consider that apart from the standard model, we have a full copy of the standard model that is related to it through a Z2 symmetry. And under this Z2 symmetry, the axion, so there's a single axion that is shared among the two worlds, and the axion transforms non-linearly under the symmetry. That means that it gets a shift of pi. So now, if we write the most general Lagrangian that respects this symmetry, what we obtain is the standard model, the mirror sector, and then the only difference is that, so both the mirror sector and the standard model have exactly the same coupling and the same spectrum and the same masses, with the only difference that the theta parameter of the mirror sector is shifted by pi with respect to that of the standard model. Now, if we compute the potential for the axion, what we find is that there are two contributions. We have the contribution of QCD, and then we have this contribution of the mirror sector that has a shift of pi. And therefore, when we add the two contributions, we get indeed a partial cancellation and therefore a smaller mass for the axion. However, the first consequence that we see from this set to axion is that now the minimum is no longer in zero, right? Now this set to axion predicts the theta parameter to be pi halves, and therefore this is not solving the strong CP problem. However, this idea of using a set and symmetry, a discrete symmetry, can be generalized to the certain axion, right? In which we have n copies of the standard model, and under this certain symmetry, the axion still transforms nonlinearly by a shift of 2 pi k over n. And again, we have n copies of the standard model with exactly the same couplings and spectrum, and the only difference is the theta parameter. Now, when we again compute the axion potential, we see that if n is an odd number, if we have an odd number of worlds, indeed we get a minimum in theta equal to 0, and therefore we can solve the strong CP problem. Moreover, one can find that the mass of the axion in this case will be exponentially suppressed. So this cancellation, it goes exponentially with the number of sectors. So this idea of using discrete symmetries in order to obtain light fields was actually proposed by Anson Hook some years ago, actually in a completely different context. He was interested in solving the hierarchy problem with this kind of discrete symmetries. And he just briefly comments that this kind of mechanism could also be used to obtain a light QCD axions. And in these projects, we have expanded on the mathematical properties of the axion, and we have studied the phenomenology, both assuming that this axion is dark matter and without assuming it. But
before going quickly about this this paper by Anson Hook, did he have an axion in this model? Did he have these n mirror worlds connected by an axion, or is this your contribution adding this axion in?
No, so he presented this idea of using discrete symmetries, right? But the model in which he tries to solve the hierarchy problem is different from the one that I told you, right? So the mechanism, the idea of using these certain words is similar, and he comments that you can also apply to the axion. But so this is maybe a 4-page paper in which he devotes like a couple of paragraphs to say you could also do it with the axion. Yeah.
Okay. But do you know if there's a way of solving the hierarchy problem with a corresponding axion of some certain properties which would allow you to confirm this solution to the hierarchy problem or something like this?
Yeah, I think it is fair to say that the specific framework that Anson puts out in this paper is more of a toy model, let's say. It's not that you completely solve the hierarchy problem, but you improve it, let's say, and it's not a full theory that.
Yeah. Okay. Yeah.
So in principle, I think one could explore that, but I think that in the side of the solution to the hierarchy problem, I think more work needs to be done to implement the mechanism in the full standard model with all the details, right? I think it's more of the first attempt and a showcase of how you can use this mechanism.
Yeah. Okay, thanks.
Yes. So let's understand a bit better why the mass of the axion is exponentially suppressed in this case due to this symmetry, right? Because in this case, we have basically n contributions to the axion potential, right? And therefore, in principle, one would expect that the mass of the axion grows with n, right? Because we have n contributions of more or less the same order. However, this is not the case. We already saw that there's some degree of cancellation between the different contributions of the axion potential. And actually, it is really interesting to understand, and it is easy to understand why there is such a good cancellation that it's actually exponential, right, in the number of worlds. So if we look at the total potential that we can see here, we are basically adding up the same functional dependence, right, because all the sectors contribute equally, with the only difference that each sector has a different shift here in the axion, right? So one can multiply and divide by this step here that we are taking in order to evaluate the potential of the QCD axion, right? And once we look at this formula, we can easily recognize that this is nothing but the rectangular rule, right? This is nothing but a Riemann sum, we are multiplying the step times the function, right, evaluated its time at a different point due to this step that we're taking. And we all know that a Riemann sum can be very well approximated by the corresponding integral, right? And then we only get some subleading terms because this approximation is not perfect, right? These subleading terms go to 0 in the limit of n going to infinity. So the interesting thing about this is that the bulk of this potential, right, this integral, does not depend on the axion. This adds up to a constant because you're basically integrating from 0 to 2 pi a periodic function, and therefore the dependence on the axion completely drops from here. And as a consequence, the total potential for the axion is fully contained in the subleading terms. That means in the error that you commit by approximating the Riemann sum by the integral. And this is why so okay, as I'm telling you, then the total potential will be contained in this error, and this is the reason why this potential will be so suppressed. In fact, there are a lot of mathematical theorems that tell us how well this Riemann sum converges to the corresponding integral. And in particular, using a bit of complex analysis, one can understand that this is related with the analytic structure, with the holomorphicity structure of the potential once you extend it to the complex plane. And when you do and you use all these powerful theorems, the conclusion that you get is that the axion mass in this framework, it is exponentially suppressed, and the parameter that controls this exponential suppression is nothing but the ratio of m up over m down. And then, okay, moreover, we were also able to obtain a simple analytical formula of the QCD axion mass in this certain axion model, right? And also we were able to show that even though the QCD axion potential has this shape with this square root of 1 minus the sine squared, when you add up all these contributions of the certain axion, you get a single cosine, and you also get this simple analytical formula. So once we know the prediction for the axion mass in this framework, we can look a bit at the phenomenology. What we find is
Pablo,
that for the... Yes?
Can I ask you a question before you go on phenomenology?
Yes, sure.
So, you know, in usual, you know, n=1 axion case, you know, in your extension, there is the people discuss usually this axion quality problem. You know, if you believe that the extra, you know, high dimensional operators violate the pitch equisymmetry and so on and so forth. What is the influence of that kind of discussion in your model?
Yeah, so this is a really nice question. So in principle, one would expect that if you're making the axion lighter, you would expect that maybe you are even more sensitive to this problem, right? Because then even if the extra contribution that spoils the solution is even smaller, maybe you are even worsening that issue, right? However, what we found is that in our case, what happens is completely the opposite. What happens is that this certain symmetry automatically protects you from dangerous operators that could spoil your Petzl quality. So then what we find is that, okay, this is in fact what I was going to show you here, right? So we presented two UV completions of this framework, and in the KSV set-like UV completion of this certain axion model, what we find is that the certain symmetry automatically forbids these operators that could break the Petzl symmetry, and therefore in all this region of the parameter space, one automatically also solves the Petzl quality problem. Yeah. So this is another motivation for this kind of framework. Yeah.
Okay, can you, well, as a follow-up, maybe we can discuss, but can you imagine this Zn symmetry, why it's respected by the quantum gravity? Is that some kind of remnant of gauge symmetry or something like that?
Yeah, exactly, yeah, because these usual conjectures, right, tell us that global symmetries, so these arguments either with black holes, wormholes, or these swampland conjectures, they tell that all global symmetries need to be explicitly broken, right? However, it doesn't say anything about discrete symmetries. As you were commenting, discrete symmetries can be can be actually a remnant of discrete gauge symmetries, and therefore gravity would respect these symmetries. So that's why, in principle, one can say that this symmetry can be respected by gravity. Yeah, exactly. Yeah, exactly. So then, looking at the phenomenology, we see that with this kind of model, we basically move the QCD axion band to the left, and therefore we can populate these regions of the parameter space with an axion that actually solves the strong CP problem, and even, for example, ALPS II could solve a true QCD axion within this context. Then I think I'm not going to have a lot of time to discuss this, but apart from this naive phenomenology that you're just making the axion lighter, there are some novel effects, novel bounds that you can put in this kind of framework due to finite density effects. The main idea is that we are getting this really fine cancellation between all the contributions, but once you are in a medium, for example, inside of a stellar object, then we know that the contribution of the standard model to the QCD axion potential gets modified, right, due to finite density effects. And since the stars are only made out of standard model particles, this breaks this cancellation, and therefore this dramatically changes the potential inside these kind of objects. And okay, I don't have a lot of time to discuss this, but due to these finite density effects, there are extra bounds that you can put on this model. Looking at data from the sun, from neutron stars in the future, and even you can also constrain this model with gravitational wave signals, because due to this modification of the potential, you can even generate a long-range interaction between astrophysical objects that modify the gravitational wave signal of neutron star spirals, for example. Okay, before going now to the dark matter part, let me say one caveat, right, that I didn't comment. That is that actually within this framework, you do not always solve the strong CP problem, because due to this set symmetry, you not only have a minimum in theta equal to 0, but actually you have n minima. And therefore, in this sense, this is worse than the canonical QCD axion model, because here one only solves the strong CP problem with a 1/n probability, let's say. So this is still an improvement with respect to the tuning of the strong CP problem of 10 to the minus 10, but it is fair to say that this is worse than the canonical QCD axion model. So now let me explore the possibility of whether this kind of framework, this kind of extremely late axion, could also explain the dark matter relic abundance. And what we have found is that due to the particular temperature dependence of this axion, we found a new production mechanism for the axion. That is what we call the trapped misalignment mechanism. So before going there, let me briefly review one of the production mechanisms of the axion, that is the so-called misalignment mechanism. If we start with a homogeneous scalar field, then one can compute the equation of motion for the axion, and it's nothing but this equation. And if you look at it, this equation is really familiar, because this is nothing but the equation of the damp harmonic oscillator, in which the role of friction is played by Hubble and the role of the frequency is played by the mass of the axion. And therefore, we can use all the intuition that we have from the harmonic oscillator to the evolution of the axion in an expanding universe. In particular, in the early universe, when Hubble is really large, the value of the axion field is frozen at a given initial misalignment. But then when the friction becomes of the order of the axion mass, then the axion starts to oscillate around the minimum. And then the important part here is that this homogeneous oscillating scalar field dilutes as matter. It dilutes as a to the minus 3, and this is the reason why this kind of wave can be a good dark matter candidate. And one really important ingredient in order to obtain the current axion relic density is the moment in which the axion starts to oscillate, because this will determine the moment from which we dilute this energy density that was stored at the beginning in this scalar field. So what about the Seden axion? What happens when you try to compute the relic density in this setup that I have presented you before? So one thing that you need to take into account when studying this mirror world cosmology is that in order to evade the bounds that you have from n effective, you need to assume that all the mirror sectors have a temperature that is smaller than that of the standard model, because otherwise the neutrinos of all the other sectors will contribute too much to n effective, right? And this imposes a bound on the temperatures of these sectors. Once you assume that the other sectors are colder than the standard model, now we can look at what is the temperature dependence of the axion potential. And what we find is that, similarly to what I was commented you with the finite density effects, right? Now, when you take into account finite temperature effects, you will see that at finite temperatures, this cancellation is broken. And therefore, at high temperatures, the potential of the axion will be large, and the minimum will be at pi. So let me show you here a little video of the evolution of the axion potential. So at high temperatures, okay, let me put it again. So at high temperatures, the potential is large with a minimum in pi, but then at lambda QCD, the cancellation gets back again, and we get the really shallow potential of the zero temperature Seden axion. So now, if we take into account this temperature dependence of the axion potential, we find that the prediction for the relic density of the axion is completely different. And this is what we have called the trapped misalignment mechanism. The idea is that the axion now undergoes two stages of oscillations. First, the axion will oscillate in the high temperature minima around pi, and it won't be until lambda QCD, when the total potential develops, that the axion will be free to oscillate around the true minima. And this early stage of oscillation effectively generates a delay on the onset of oscillations. And this delay of the onset of oscillations means that the axion relic density has been diluted for a less amount of time. And therefore, the relic density in terms of axions is enhanced. We get more dark matter than expected. Moreover, in some regions of the parameter space, we also realized that this Seden axion also constitutes let's say, a UV completion of the recently proposed kinetic misalignment mechanism. The idea is that after the first oscillations around the minimum in pi, the the axion velocity can be large enough so that then when this shallow potential develops, the velocity can be large enough for the axion to overcome several of the potential barriers. And since the axion overcomes a lot of these barriers, then the true onset of oscillation is further delayed. And therefore we get an even enhanced relic density. And this idea of having a large axion velocity was actually proposed, I think, like it was a couple of years ago, like quite recently, in the context of different models, right? With so they were proposing an Affleck-Dine-like mechanism in order to generate this large axion velocity. And what we find here is that an early stage of oscillations combined with this non-adiabatic modification of the potential can be another way of triggering this axion velocity. So now, once you take into account all the different regimes, what we find is that one can explain 100% of the axion relic density in this purple region of the parameter space. And then this different behavior corresponds to the different regions in which one of these, either the trapped or the trapped plus kinetic misalignment, is active. And as we can see here, this is really interesting because we predict that this certain axion will be actually observable or tested in all these future experiments. For example, even IAXO will be able to test in some regions of the parameter space this certain axion. So now that we have seen the phenomenology, we can go back to the questions that I asked at the beginning that were, and see how this changed in light of this new mechanism, right? So the first one was, could Casper Electric detect an axion? So now, in light of this certain axion, what we find is that now there is no longer a one-to-one correspondence between the axion coupling to the EDM and the axion mass, because now this is not the only contribution to the axion mass, but we have all these extra contributions that generate a lighter axion. And therefore, since we are actually moving this band to the left, a positive signal of Casper Electric phase 1 indeed could be interpreted as a QCD axion, but only within this kind of paradigm in which you have extra contributions that cancel the axion mass. So then, in light of this, the certain axion could be tested by even Casper Electric phase 1. Then, regarding the second question, that was, can the QCD axion be fuzzy dark matter? Again, we see that within this framework, we can actually explain the dark matter relic abundance, even in this region of the parameter space, in which the QCD axion has masses of the order of 10 to the minus 20, 10 to the minus 21, the region that corresponds fuzzy dark matter. So in this sense, the certain axion would be the first fuzzy dark matter that actually solves the Strong-Seeley problem. Okay, and with this, I am done with these two works regarding an extremely late axion. And now in the last part of the talk, I want to briefly comment this idea that I've been working in the past month. That is that we realized that phaser can be used as a light shining through wall experiment. So before going there, let me tell you that the light shining through wall is an idea in order to detect axions that has been used in the past, right? And the basic idea comes from the following property of the axion. So if the axion couplings two photons, due to this axion FF dual coupling, one can see that in the background of a magnetic field, the axion and the photon mix among each other. And therefore, once one can compute the physical propagating states, and what one finds is that the axion and the photon can oscillate from one into the other, similarly to neutrino oscillations. And this kind of property, this phenomena in the axion, is exploited by these kind of experiments by shooting a laser to a wall. And the idea is that if you put a magnetic field at both sides of the wall, then this laser that you're shooting to the wall could convert into axions, and these axions, or could oscillate into axions, right? And these axions can freely penetrate through the wall. And then these axions can go back and convert into photons that then are detected at the other side of the world. So then effectively, light has penetrated, has shined through the wall, right? And in particular, there are several experiments that are trying to use this technique in order to look for the axion, like, for example, ALPS II here at DESY, that in the following will really go down in terms of the axion coupling to photons and explore completely new regions of the parameter space. So now let me briefly comment you about what is phaser, right? So so here I have a plot of the LHC in which this blue line that you can see here is part of the LHC, right? Where the protons are going around, right? And you see that this starts to curve here, right? And here in this point is where we have the collisions of the protons. And it is where ATLAS is located. And what ATLAS is looking for is to see the particles that after the collision of the protons that come from here and from here, ATLAS looks at the particles that go in the transverse direction, right? However, it was recently realized that actually after the collision, most of the particles that are created don't go in the transverse direction, but actually go ahead in the forward direction, right? So they follow this red line in the forward direction of the beam. And due to this, it was recently proposed to make an experiment that is called phaser, in order to exploit, for example, explore or try to prove long-lived particles. So one thing that one could explore with phaser is particles that are created in the collision here, that then propagate in the forward direction, but are long-lived and then decay in this phaser detector. So the main purpose of phaser was to look for these long-lived particles, and for example, they have even been able to detect neutrinos from the LHC, which I find quite impressive. So what we recently realized is that phaser, without making any modification of the current experimental setup, is automatically a light shining through wall experiment. The reason is that in the collisions of the LHC, a large flux of high energy and high intensity photons is created in the forward direction. And then on top of that, within the beam of the LHC, we have a lot of magnets that are used to confine the beam. Then we have a big piece of rock that are basically the LHC absorbers that are used to filter all the radiation that is generated after the collision. And then in the experiment phaser, they have an spectrometer and a calorimeter with magnetic fields and a detector that can detect these high energy photons. So without changing anything at all, phaser is a light shining through wall experiment that could explore axion-like particles and axions. So looking at the projections and the regions of the parameter space that one could explore with phaser, the first disclaimer that I have to say is that the regions that phaser will explore are already excluded by either helioscopes, astrophysical arguments, or cosmological arguments. However, phaser will in the next years provide the first purely laboratory-based bounds on some regions of the parameter space. And in fact, several, okay, so let me explain. So here I am plotting in blue the projections that we saw, that we computed from this light shining through wall at phaser, right? And for example, one can compare it with ALPS II that you can see here. And what we see is that phaser benefits from these really high energy photons, and therefore it is able to prove higher masses, right? That's why this is displaced to the right, because we can keep the coherence of these axion photon oscillations even for higher masses. Of course, we don't reach such good sensitivities as ALPS II because we cannot benefit from an experiment that has already been thought to do a light shining through wall, and also because one cannot use resonant cavities for such high energy photons, for example, and we don't get such a good sensitivity. But still, I think it's interesting that this experiment, completely for free, will be able to explore these regions of the parameter space that have not been explored by any other laboratory-based experiment. Of course, I have to say that I don't expect an axion to appear here, but it is good also to look, right? Because we can get surprises. For sure, if phaser detects an axion here, this would be a really big surprise that will force us to rethink how we understand astrophysics, right? Or the properties of the axion. Okay, so with this, I am already done, and let me conclude. So in this talk, I have presented you a proof of concept, right? So I have presented you that at least there is one mechanism with which the QCD axion that solves the SON-CP problem can be lighter than the canonical axion paradigm. I have also commented that at least within one of the UV completions that we explored, the Peccei-Quinn symmetry can be protected, and therefore one can solve the so-called Peccei-Quinn quality problem. This kind of action motivates interesting regions of the parameter space that will be proved in the near future by experiments like ALPS II, by the AXO, etc. Moreover, we also found that this axion can actually explain dark matter in large regions of the parameter space, and that the way in which the axion dark matter is produced differs from the canonical misalignment mechanism, and we found this novel trap misalignment mechanism. That, moreover, in some regions of the parameter space can source the so-called kinetic misalignment mechanism. Then regarding caveats and outlook, so of course this framework is non-minimal, right? Because you have to assume the existence of these n copies of the standard model. So it would be interesting to explore whether this framework can be embedded in a more complete UV setup, maybe with extra dimensions, maybe this can arise naturally from strings. Similarly to, for example, in the case of clockwork, that the existence of all these scalars can be understood like an extra dimension, right? Of course, then one of the caveats is that we only solve the CP problem with a 1 over n probability. Then regarding the trap misalignment, there is still much to explore. First of all, in this study, we have only focused on the zero mode, and in principle, one should also study the higher modes of the axion, right? In general, the fact that you're exploring non-harmonic parts of the potential implies that you can excite higher modes of the axion. This is what it is called axion fragmentation. And in fact, some colleagues here at DESY are finishing now a study in which they study both what is the impact of axion fragmentation on both this trap misalignment and also the general kinetic misalignment, right? And then it would also be interesting to explore how the trap misalignment arises in other scenarios, right? This could be used in generical dark matter or also to generate a Keynesian area, etc. And with this, I am done. So thank you very much for your attention. Yeah.
Thank you. Thank you very much for that. A really well presented talk. We have some questions. I see Victor has his hand up. Do you want to ask?
Yeah, I have a question because I've seen your diagram limits on ultralight axion. And actually there are plenty of measurements already, at least 3 of this ultralight axion using measurements of electron dipole moments. Actually, you mentioned it. Yes, you mentioned it. Is it suitable area? It's NEDM, Casper, and there is also new results from Eric Carnell group in molecules.
Okay. So so what you're saying that there are new results from these experiments. Okay. So I'm using the plot from already.
No, I haven't seen new results from this experiment. But okay, you mentioned results from Casper, and there is results from Eric Carnell group also. It's it's a Nobel laureate, Eric Carnell, who is measuring electric dipole moments in molecules. Okay, just so it's relevant. This area is relevant for your work. All I want to ask, yes.
So these are already bounds, right? And what you can see here in light blue are the prospects of Casper phase 1, phase 2. I don't know if this was your question. So
yeah. I just probably missed this part, so I have not seen it. So, but it's relevant to ultralight axion, and
So,
about
but of course, this only So these bounds on the NEDM do not apply to a generic fuzzy dark matter, right? They apply to our model because our also solves the strong CP problem, right? And therefore also couples to the EDM, right? So maybe that's the reason why in other plots maybe you have not seen this, right? Because if it doesn't couple to the EDM, then these bounds don't apply to other fuzzy dark matter actions, right?
Yeah. Well, only if you are interested, there is a new. This is most recent result is Gila Eric Carnell group who made limits on axion in the title of the paper was 7 orders of magnitude range. For small masses, 7 orders. It covers a big range of masses, and it's also related to this plot. That's all. Okay, thank you.
Thanks.
Anyone else? maybe I can go quickly. Can you talk a little bit more about UV completions? Because did you think about perhaps like a DFSC like model, or perhaps a model with like a domain wall number greater than 1? I wonder if that would you have this kinetic misalignment, whether this would sort of help rescue from domain walls and things like this. Did you think about other UV completions?
So actually, in the paper, so we tried to have a UV completion with it all the canonical invisible axion models, right? You have the KSV set, the DFS set, and the composite axion, right? And we succeeded with both a KSV set like axion, right, set and axion, and with the composite axion. However, with the DFS set, we were not able to implement this set and symmetry with the 2 Higgses of all the sectors. We tried, but maybe it is possible, right? But we were not able to implement the set and symmetry consistent with the gate symmetries of each sector. Yeah. And then regarding so something that I didn't comment that it is also relevant is that as you were commenting, this in any setup in which you have kinetic misalignment, in principle, you could worry about domain walls, as you were saying, right? Because what can happen is that if your initial conditions at the beginning of the oscillations are slightly different in different regions of the universe, then through this kinetic era, right, you can end up on drastically different minima in different regions of the parameter space, right? And you can generate domain walls, right? So in fact, this is also being explored by these colleagues at DESY, and it really depends on the specific framework whether you introduce a domain wall problem or not, right? Because also what happens is that the early stage of oscillation also forces you to go everywhere in the universe to a particular point in field space, right? So then depending on the initial fluctuations that you have, you can or not have a domain wall problem, right? So this is something that, yeah, deserves like a full study, I would say.
Yeah. Can I ask another question? Now, presumably this is naive, but look, so this axion usually, mixes with pions. So now it mixes with the mirror pions and so on and so forth. Would not you expect some kind of exotic processes in, I don't know, kaon mixing with a mirror kaon and things like that?
But yeah, so we also thought about that, but at the end, what happens is that these other sectors are completely secluded from the standard model, right? And the only connection between the standard model and these sectors is through the axion, right? So if you want to think about any effect that involves the axion and also these mirror sectors, automatically will be suppressed by both the coupling of the, so at least 2 powers of 1/FA, right? Because you first have to couple the axion to the standard model, right? And then to the other sector, right? So we thought a bit about that, but I don't think there is leading phenomenology in that sense, right? It is most important, all these effects that you have, for example, as I was commenting from finite temperature, right? That you are only canceling one of the contributions, or then all the usual phenomenology of the axion, yeah.
Yeah. Okay. I don't quite understand, your answer about the domain wall. So you have this degenerate Z vacua, and you claim that the solution is 1/n probability. But the typical thing about this formation, if the patches are causally disconnected, you can end up anywhere, and then there is a domain wall, right?
Yeah, exactly. So of course. So if you are in the post-inflationary scenario, this model has a really dangerous domain wall problem that then for you, that's a big problem, right? Yeah, for sure. Okay, maybe I was not clear enough. What I was saying is that even in the pre-inflationary scenario, in which you start with a homogeneous field, the fact that you have this kinetic misalignment in principle could be dangerous, right? Because what happens is that even in the pre-inflationary scenario, you have isocurvature fluctuations of the axion, right? That typically those are not enough to generate you a domain wall problem, right? Because they are really small, and then you are always ending up in the same minimum. However, if you have these small isocurvature fluctuations and you combine them with this kinetic region in which the axion velocity will depend on this really specific initial misalignment, then you can reintroduce the domain wall problem, right? And it is there where it really depends, and in some cases you don't have domain wall problem, and in some cases you do reintroduce it. Yeah, so maybe it was not.
I see. So this scenario with the exact Zn cannot work below the inflation, post-inflation, in principle, or?
Yeah, exactly. So I don't think it can, right? So in fact, something that also I was commenting with some colleagues here that I think it has not been explored, right, is that topological defects in this kind of framework have to be really funny, right? Because you would have here, in fact, it has already been commented by a recent paper by the people that proposed the kinetic misalignment. They, in one of the recent papers, they talk about these rotating axion strings, because in this is what you would expect here, right? And actually, I think that deserves a full study, right? I think this is something that needs to be explored, right? What happens with the topological defects in this system in which you could have domain walls, axion strings, but rotating axion strings, right? I think that's, yeah, it's difficult to predict what is the outcome of all this network, right? It will be non-perturbative, and yeah, I think that deserves a full study.
Okay, thanks.
Pavlo.
Yes.
Hello, can you hear me? I was wondering, like, there was like a slide that said that this model doesn't always solve the strong CP problem, and it's like a 1 on n probability. Can you explain like why it's 1 and like why does it not always solve the CP problem?
Yeah, because so you can see it here in this plot, right? So here you see the axion field, right? And usually the minimum is at 0, right? In the usual case. Yep. And that's the only minimum of the axion potential. However, within this framework, the axion potential has n minima that you can see here. And only one of them predicts that the theta parameter is actually 0. In all the other points, then the value of the theta parameter that you predict is 2 pi k over n, let's say.
Okay.
Then the 1 over n probability comes because when the axion is rolling and it's going over all these barriers, at some point the velocity will be, will get smaller and smaller, and at some point the axion will be trapped in one of the minima, and the specific minima in which it will stop, it will be completely random among all these n number of minima, and that's why you get a 1 over n probability of ending up in the good minima, right, that corresponds to theta equal to 0.
Okay.
Mm-hmm. Yeah.
Thank you.
Thanks.
Did anyone else have any final questions? Michal?
My question has been already answered. It was about actually the offset n, about the different minima and topological defects.
Great.
Perhaps I can ask one final one before maybe we stop the recording. Is about because it'd be nice to hear more about the light shining through wall with phasor. So this signal that you'd see, I mean, you know that you're looking for axions which would sort of ostensibly be ruled out by the stellar bands, but wouldn't the signal here look kind of like any other particle decaying to photons?
Yeah, exactly. So in fact, so what we are saying here is that the phasor experiment was already going to explore, for example, heavy axion-like particles that decay into photons, right? So the message that we're given here to the experimentalists is that apart from doing a search of a 2-photon search, right, you should also look for a monophoton search, right? Because here what we expect is a single photon, a single high-energy photon, right, that comes after everything. Yeah. So that's the key difference. Yeah.
And would that be a unique signal? Or would there be other long-lived particles you might expect a single photon from?
Yeah, so regarding, yeah, so of course a relevant question is what happens with the background, right? So in this kind of experiment, there would be there could be two backgrounds, right? One of them, because so here you have this big rock that basically filters almost everything, right? But there are still 2 backgrounds, right? One could be neutrinos, right? However, this can be, the signal that you get from the neutrinos can be easily disentangled, right? But then the other thing that really goes through the wall are muons, right? Muons can perfectly go through this wall, right? And then when they are in the spectrometer, they can radiate a photon that will also be a high energy photon, right? And this could perfectly mimic the signal that we're looking for. However, phaser has these vetoes, right? These muon scintillators, and it seems that they are confident, there have been already these studies of the background, and they are confident that they can distinguish all the photons, all the muons that go through, and therefore one would be able to really see whether that photon comes from the muon. So as far as we know, this would directly, we can assume basically no background in this case, and this would be able to constrain the axion. Then you were saying whether other new physics can also generate the same signal.
Yeah.
Couldn't you have a heavy neutral lepton which decays into neutrino and a photon? So you have missing energy plus a photon. And I'm not sure how well they can measure the directionality of the photon.
So here everything is, so you have to take into account that here everything is super boosted, right? So everything goes in the beam direction, right? So there's no, that is not of much help, right? Because from whatever you generated, it will go in the same direction, right? So I'm not sure if there's other new physics models that could generate something similar. Maybe it is. One thing that, so there are some ideas that one could use in order to disentangle that this is really an axion, right? One is related with a paper that Kieran wrote recently, right? That is the one of weighting the solar axion, right? So in this case, if phaser gets a signal in the region here, for example, then one expects that if we get enough photons, let's say, one expects that the signal actually depends on the frequency of the photon, and therefore one would get an oscillatory spectrum for the photon that comes from this axion photon oscillation, right? So of course, in order to do that, you need a lot of statistics, right? But the energy resolution of phaser is really good, right? It's smaller than 1%. So in principle, one could look for this oscillatory behavior of the spectrum in order to see whether this comes from an axion, right? Another thing one could think about is that the photon that comes from the axion is expected to be polarized in the direction of the magnetic field. However, it seems, so the colleague with which I proposed this is actually one of the scientists that proposed phaser, right? And we were discussing whether one could detect the polarization of the photon, and it seems it is not easy, right? So we don't know if that could be done. But another difference from maybe other new physics that generates this single photon is that if it comes from the axion, it has to be polarized in the direction of the magnetic field.
Can you run the phaser with a different magnetic field strength? Could you tune the magnetic field? Because that would also change whether you have a signal or not. Or do they need the magnetic field for the experiment to work?
Yeah, so okay, so here what we're proposing is to use everything that is already there for other purposes, right? So these magnets here are the magnets that are used in the LHC to confine the beam, right? We are saying, okay, this is already is useful for us, right? And then the magnetic fields of phaser are actually permanent magnets, and so they are using them for other purposes, right? So it's not that they're going to change them because we tell them that they can look for this, right? And in fact, those are permanent, right? So one wouldn't, it's not so easy to slightly change them. But then in the forward physics facility that will be done later on, I think that they're not going to use permanent magnets, but still they're going to use electromagnets, right? So maybe they're going to use coils. So in that sense, maybe it is easy to change the magnetic field. Yeah.
All right. Well, maybe I can stop the recording.